Hello, moving on to chapter 7. So this one's about alkenes and alkynes. So sometimes you actually hear them referred to as olefins. It's an older name, but that's sort of I guess you can think of it now as a nickname. It actually comes from the Latin for to make oil, stuff like that, because if you were because they are a component that you can use to make longer chains to make the oil, stuff like that. So make alkanes. Stuff like that. So first off, we were talking about the cis and trans isomers, and so for alkenes you can have both the cis and the trans, right? So if remember with cis is always either up, up, or down, and then trans is always one up, one down. Okay. With cis and trans on an alkene, I don't necessarily always look at those two groups. I just look at the hydrogens. That's the easiest thing to look for, because with cis and trans, you're going to have one hydrogen on one side, one hydrogen on the other. That's the only way you could have it. If you've got more than that, then you either you don't have. If you had a hydrogen here and hydrogen here, there's no difference between them. They have to be different. If there's fewer than two hydrogens, then you need to go to a different system, which we'll talk about a little bit later. Stuff like that. So, but yeah, you just look at how the hydrogens, they are pointing away the same way away from the double bond, stuff like that. So in this case, they're pointing down. Here, this one's pointing down, and this one's pointing up. So this one's trans. Okay. If you don't have the situation where you have a hydrogen on each carbon, but then you need to go to the E and Z method. You can always do the E and Z method, even if you have those two hydrogens. It's just cis and trans is a little bit easier to talk about. So for that, but this is a much more general situation, or general naming. Okay, so what we're going to do is we're going to take our alkene. Right, so we got the four things hanging off. We're going to take it and only look at one carbon at a time. So we're going to look at this side, and then we're going to hang it off. So see what's hanging off of that carbon, and then see what's hanging off of that carbon. And actually, what we're going to be doing is we'll be ranking them, ranking high-low, and then high-low. So there'll be just that's all we need to do. We don't have to do 1, 2, 3, 4 like the R and S. It's just high-low on the left side, high-low on the right side, and that's it. Stuff like that. But you look at these independently. We're going to use the same Kahn-Ingold-Prelog rules that we use for R and S to set priority. We're going to start walking out just like we did with the R and S. We'll start here, see what's attached, and then if that's a tie, then we're going to move, look at bonds. If that's still a tie, then we move out one more and start the process over again. Okay. Now, if the high priority group, so you say, okay, well, this is this is high and high-low, and this is high-low, right? It's given a Z designation. Okay, if you end up with your highs on opposite side, so the high up here and the high down here, this is E. Now the letters come from German, stuff like that. So the German for for any Germans out there, zusammen, which means together, because they're on the same side. So with that, so if the higher priority is on the opposite side, so basically like here and up and down, is like a trans situation, it would be E. Now I always thought it was a quirk that the Z looks like it's going the opposite ways, and the E looks like it's going the same way, stuff like that. But that's one of those little quirks. It's actually flipped. The other way you can think about it is break out your bad German accent, and you can say are the high priorities on the same side, some of that. So that's the way you can think of it. Are they on the same side? Yes, then they are Z. If they're not, then they're E. So this so high. The higher priority ones are facing the opposite way from the double bond. Here they're facing the same way in the Z. So, okay. So for this one, all right. So we're going to take this. We're going to look at that carbon first, and here, right? We're looking at carbon versus hydrogen. So this is going to be the high, This is going to be the low, right? We just use the same rules, right? We're looking at this carbon and that hydrogen. On this side, right, we're looking at right, it's a CH2 here. So for this side, it is carbon versus chlorine, right? So here, excuse me, this is going to be the high. That's going to be the low, right? So this on this side, the high is going up. On this side, the high is going down. They're not on the same side, so it's E. Okay. This one here, OH. Okay, so for this one, it's so we're looking at this carbon first. So you can ignore the ones on the right. This one, it's carbon versus carbon because that's a CH2. Now this one, right, it has 1 carbon-carbon bond, 3 carbon-hydrogen bonds. This carbon here has 2 carbon-carbon bonds, 2 carbon-hydrogen. Okay, and look at the heaviest bond, it's carbon, but this one has 2 of it, so that means that this is going to be the high side. This is going to be low. Okay, on this side, again, you have carbons. This is a CH2. This is also a CH2. Okay, so if you look on this side, right, 2 carbon-carbon bonds, 2 carbon-hydrogen. That one there, it only has 1 carbon-carbon and 2 carbon-hydrogen, but it also has 1 carbon-oxygen bond. So you compare this one to that one. Even though this has 2 of it, that doesn't matter. This is, you look at the heaviest bond, and so it's down here, so that the high is here, low is up here. The highs are on the same side, and so so it's Z. And every time I think about doing that little joke, it's I'm sure my German grandmother is rolling over in her grave. So like that. So it's E and Z. So actually, she would have found it hilarious. So she's my great grandmother. So okay, so for relative stabilities for alkenes, okay, in general, the trans alkenes are going to be more stable than the cis alkenes, and we'll talk about a big exception in a minute. And it's all about sterics. Okay, so if you have the hydrogens on this one side, right, they're going to be tiny. All the other groups are going to be a lot bigger than those hydrogens, and you're going to get steric clashing here. Stuff like that. And so, but on the trans version, the large group here is going to be next to a hydrogen, so you relieve that strain. So in general, trans alkenes are going to be more stable than cis. The exception are the cyclic. Okay, and so that's, and if you notice, whenever we put a double bond in here, these groups are trans, right? So that there's going to be a hydrogen here, they're pointed the same way from the double bond. So that makes it trans, and the steric clashing is lost because it can because of the twisting that can happen around these other bonds. You can twist out of it. What is it? So for the trans, this is probably about as small as you can get to get a productive trans cyclic compound, and if you try to do this with your model kit, hopefully you won't break your model kit. But notice how oddly shaped it ends up having to be. So with that, right, there's a hydrogen pointing up on this side, there's a hydrogen pointing down on this side. It's trans, but it's going to be really difficult. So for cyclics, you end up with the cis. Okay, so for heats of reaction, we can actually, whenever we burn these things, we can measure how much energy is given off. The more energy that's given off, the less stable the compound is. Okay, so if we have this butane here, where the double bond is at the end, right? We have a big jump. We have quite a bit of energy when we burn it. If we put it inside, sort of internally, not at the end, so that we get less heat coming out, right? So that means that the double bond not at the end is going to be more stable. But this is the cis version. The trans version is actually going to be even more stable, right? So because you don't have the steric clashes of these those two methyl groups there. So this is heat. So the more energy is given off, the less stable the molecule. Okay, and so really it's what's going on is it's more substituted. Okay, so you can sort of think of it, the fewer hydrogens you have on that, on the double bond, directly on the double bond, the more stable it is, okay? And so this one here, right, this is completely unsubstituted, so there's just hydrogens. That's going to be the least of them, so for ethylene here. For here, you get more stability, right, because you only have 3. Here you have 2, 2, 2, 1, and then none. So increasing stability as you go in here, fewer hydrogens directly on that double bond. Okay, so for here, right, this has 2 hydrogens hanging off of it. With that, so 2 carbons on this side, 2 hydrogens on this side. Here, if you on this side, you only have a two carbon bonds, and only 1 carbon-hydrogen bond here. This has 1 hydrogen hanging off the double bond. This one has 2, and so this one is going to be more stable. Okay? And we'll talk why that is in a second. So one way that we can make the double bonds is through this the use of a base, stuff like that. And so you can use the alkyl halides. You can use this as a leaving group, but you kind of do it internally. And so what ends up happening is if you rip off this hydrogen, these electrons can collapse down and kick off the leaving group. And so the electrons here that were in the CH bond can become this new carbon-carbon double bond here. Okay, the other way that you can do it is, well, essentially the same thing. If you throw an acid, you can actually turn the OH into a good leaving group. And then it goes the same thing. This hydrogen gets ripped away, these 2 electrons collapse down, and then this is the leaving group after it's protonated because it leaves as water. So, okay. So this one here, when you're dehydrohalogenation, okay, so you're leaving, you remove a hydrogen and a halide, that's why dehydrohalogenation, okay, so that they have to be right next to each other because you're going to make a carbon-carbon bond, okay, you can't make a carbon bond all the way over here, so it has to be right next door, so a base is going to come in, grab that hydrogen, those electrons are going to collapse, this carbon can't have a 5th bond, so it's going to push away. So it goes like that, just like an SN2, just like in where as this 5th bond is getting formed, we have to break one, and it's the one that you're going to break is going to be that halide, or the leaving group, I should say. So for here, right, so you have your base, comes in, grabs. So if you have, right, right, so here's your leaving group here. Your base in this case is ethoxide, CH2OH. Right? It's going to grab that hydrogen. It's going to take one of these sets of lone pairs. This down a little bit so you can see. And take one of these sets of lone pairs, make a bond with that hydrogen. Okay. It's just a classic acid-base reaction. These electrons can collapse down. Okay. And then we can't have a 5th bond to that carbon, so then we break this here. Okay, and so one of the classic questions is, well, why doesn't it take that hydrogen? Well, if it does, okay, it won't really have anywhere else to go. Okay, so let's say Br. So if this were to grab this, we would end up with a situation. Move those electrons there. We would end up with a carbanion here. Okay, once it's 4 bonds, this carbon here. But if it were to go here, right, to make a double bond, you'd have to break a carbon-hydrogen bond. Okay, same goes with this one. Okay, if you were to collapse it down here, you'd make a double bond with that bromine, and that's not going to be particularly happy because that would cause the bromine to have well, let's see, it'd be 1, 2, 3, 4, 5, 6, 7, 8. It would break the octet, right? Because it already has this octet. You put 2 more electrons in there, and be to 10. It's not going to be particularly happy about that. So there's no way for the molecule to deal with the hydrogen if these 2 electrons if that gets ripped away, there's no place to put those electrons. Here, at least, when we rip it away, we can collapse it down to make a double bond, and then just kick away the bromine, and so CH3. Okay. Same thing goes with here. You come in and grab this, that collapse down, kick off the bromine. It doesn't matter which one you take in this case because the molecules are symmetrical. You would end up with this product. Okay, now the mechanism for this reaction, unfortunately I don't have my model kit with me, but one of the things that has to happen is this hydrogen here has to be 180 degrees from your leaving group. Okay, so these electrons can essentially do a backside attack, just like an SN2 reaction, to kick off the halide. So backside attack, bang, kick off the halide, just like an SN2. And this is what's called an E2 reaction. Okay, so because it occurs all in a single step, the base attacks, collapse, kick away. So if you notice, the SN2 and the E2 all happen in one step. So if we go to so if we go to an E1 mechanism, right, which we'll talk about in a minute, that's going to be like the SN1, where it actually happens in two steps. So the 2s happen in one step, the 1 happens in two steps. Go figure. Okay. Now there is going to be selectivity here. Okay. So for the previous reactions, the molecule was symmetrical. So no matter where it took the hydrogen, you would always get the same product. But if the molecule is asymmetric like this, around where the halide is, you're actually going to get a mix of products. Okay. So this is hexane. So the iodine is here. Okay. So when you add base, okay, so in this case it's CH3, like that. So what we need is at least one CH bond that the base can rip away. So here it's CH2, right? Here it's CH2. This is CH3. So the base could come here, rip, collapse. If it did that, it would make this double bond, right? H's are still there. Well, there is an H here. Okay. If instead the base took this one, you would collapse it down here, and so the double bond would be here. Right? So again, there's a hydrogen here, hydrogen here. If you notice, what we're doing is we are reacting on either side of where the original leaving group is. So here's where the leaving group is. We go on the left side, we go on the right side, because there's hydrogens on both sides. So, okay, so the question becomes, which is the major product? Now you don't have to calculate what the yield is. That's not easy to determine. Stuff like that. So, but you can tell which one's going to be the major product, okay, by again looking at how many hydrogens are directly on this double bond. Okay, it's all about stability, which is going to make the more stable alkene. Well, for here, right, we've got two hydrogens. For here, we have 1, 2, 3 hydrogens. Okay, so that means you want the fewest number of hydrogens because you want the most stable alkene. So this is going to be the major product. Okay, this one right here. These are what are called Zaitsev's rules. Okay, about that. So you want to see the side. You can either think of one of two ways. You can either see the more substituted side, so it's got more things hanging off, but you can also just look at the hydrogens. It's just looking at it the same way. The same thing works with if you're doing dehydration. So you're going to turn at acid. You're going to turn the OH into a leaving group, and then you go about it the same way. Okay, but again, you're going to be making the side with the fewest hydrogens. Now, for a lot of these reactions, we like to find a complementary one. Because what if we needed this product, which normally would be the less favored product? We need that for our synthesis. Well, there actually is a solution. You just make the base really, really, really big. And so make it so big that it can't actually get over here. There's steric clashing to be able to get over on this side. And so what it does is it takes what it can. It takes it from this methyl group, and you get mostly this product. Okay, so if you want a little base, you'll get on this side, and little, I just mean there's not very much not very many atoms. It's isolated. There's just not a whole lot of steric bulk around it. Here you're going to have, like for this one is potassium T-butoxide. It's a classic big base. This is huge, and so the only way it can get, it's most likely to get on that side, on the less substituted side. Okay, so for this, right, you've got Br. So we have OH minus. Okay, the sodium is just a spectator ion. So what you're going to do is you're going to say, is there a CH bond here? Yep. Is there a CH bond here? Yep. Okay, so that means we're going to have to go on both sides. So if we react here, we're going to collapse, kick away, and we're going to make this product here, right? There is a hydrogen here, right? So you get a hydrogen, hydrogen, hydrogen. If instead you were to come in here and grab this, collapse, kick away, right, you would make this product, right? And so this one would have the hydrogen there, right? So this has one hydrogen, this has, right, 3 directly on it. So this would be the major. Okay, so for this one, okay, so there is a CH bond here, right? There's a CH bond here, right? Because it's CH3, and there's a CH bond there. So we can go 3 different ways, actually. So if we add OH minus, right? If we react here, collapse down, kick away, you would get here. So if we were to go take that hydrogen, collapse down, kick away, you would get here. And if you were to do this one, collapse down, kick away, and you would end up with that double bond here. And if you notice that the leaving group is here, here, and here, we're just going on all the sides right next to that double bond. We had hydrogens that we could rip away. We can do this. So here, right, this one's going to have 1 hydrogen. This one's going to have 2 hydrogens, right? So this is 1 hydrogen, 2 hydrogens. Here we have 0 hydrogens, right? It's all carbon-carbon bonds. So so this is going to be the major. Okay. So with that, so that's the major product. Now, if we had done this same reaction, and there was say another CH3 group here, we couldn't make this product, right? So it could only go, so chlorine, you could only react here and here. So you'd only get these 2 products if there was an extra methyl group coming off here, because you have to have a hydrogen for that base to react. Okay, so it would not be able to react there. Now again, this is the bond has to be 180 degrees, or the hydrogen has to be 180 degrees from that leaving group, and that's what's called antiperiplanar. Okay, and so if you look at this in a Newman projection, okay, so your leaving group is here, right? Hydrogen, hydrogen. But the hydrogen that actually gets away, it has to be like this. So if this is the one that the base is going to attack, it's going to go here, collapse down, kick away. But they have to be 180 degrees from each other. Okay? This is going to be with normal chain reactions, or normal chain molecules, right? You can get free rotation around that bond, in all of the bonds. With the cyclohexanes, you're not going to be able to do that. Okay, you're going to get, you can go chair flip. That's all you can do is chair flips. Okay, and so with here again, you're going to have a 180 degrees, right? So look at this Newman projection, right? This hydrogen, this axial hydrogen's up, this axial chlorine is down. So with that, they're right next to each other. If this gets ripped away, collapse, kick away. Okay. So if you look at this, so the neomethyl chloride. So if we're going to, we need to, yeah. So for this one here, right, we're gonna have up and down, right? The axial is gonna be, this one's gonna be down, okay, because it points to either the up or down on the axial, so it's pointing down. So this one here, let's be a hydrogen. There, the CH3 group is up because it's on a wedge. 2, 3 here. Again, the carbon-carbon bonds are pointed down, so that means the axial is down. So here, with this chlorine, that's pointed down. And for here, the carbon-carbon bonds are pointed up, so that means the hydrogen is up because our thing is on wedges. So here it's a isopropyl group. Okay. So for this one, and notice here you've got the axial up and that. So for this, so if you have to look, so the group has to be an axial. Okay? So a base can react here because this is axial, kick away, and you would make this product here. If you reacted on this side, you could collapse down and kick away this way, and so you would make this product right there. And because this one has, wow, they both have two. Actually, no, this one has, right, this has a hydrogen, that has a hydrogen. This one only has one hydrogen, so this would be the major product. Okay. Okay. Now if you look at the other way you do it, so just moving the chlorine up here, same molecule, but now we're going to have the chlorine start at the, because we're having it up, we're going to have it go in the equatorial position, CH3, isopropyl. This has to be 180 degrees from this, and so if you look at this, so what's 180 degrees from here? It's actually this bond here. Okay, we're not going to be able to break that. So what we have to do is we have to do a chair flip first. Okay, so we're going to go move this axial because it's equatorial now. This it's here, so this one here is axial down, so it's going to be axial axial up. This is equatorial up, so it's going to be axial up. And here, this hydrogen here goes equatorial, and the isopropyl group goes axial down. Okay, so the problem is going to be there's no hydrogens here. Okay, the hydrogen is here, but you look at axial, this isn't going to work. Okay, so the only product you can do is to use this axial hydrogen. So the base can only take this one, collapse down, kick away. So you're only going to be able to make this product here. Okay. Only that product. Now there is an E1 reaction. Okay, so with that, so it works similarly to the SN1. Okay, so with that, but instead you're going to get a double bond. Okay, just like the E1 reaction, right? The first step is the leaving group leaving. It's the exact same step as the SN1. So with that, and you leave behind this carbocation, and so instead of the, so in this case it'd be solvent, like a, methanol or something like that. Instead of having, for the SN1, having the solvent molecule nucleophile come in and attack to make the alcohol, instead the solvent would come in and react as a base, and then you would rip this away and these electrons could come around to make this double bond. Okay, so this CH bond becomes this new carbon-carbon bond there. With that, so it's the same product, but the process is going to be a little different. The mechanism is different. Okay, so how are you able to differentiate between the two? If a reaction is substitution or elimination, now for my test, I'm going to tell you. I want to see what the E2 product is for the SN2 products. But it's good to know that which one is which. So for primary halides, you're going to need to use you're probably going to get mostly SN2, so that with small primary halides. Okay, as you put bulk near it, so it goes to secondary, you've got more bulk. It's going to be harder and harder for the nucleophile to come in here and do a backside attack. Okay, so you're going to so instead it's going to take what it can and just do an elimination reaction. So for that, with tertiary, there's no way you can do an SN2 reaction. You might be able to do a little bit of an SN1, but the hotter it gets, the more likely it is that you get a E2 mechanism, where this just acts as a base, rips this away, get elimination instead of the SN1 product. So it's pretty tough to do to get this, and particularly if everything is small. So your small primary carbon with the leaving group, small base, you can do SN2. If it gets any sort of bulk to it, so your secondary carbon or with the leaving group or a slightly larger base, isopropyl, you get an isopropyl group on there or something like that, you're going to favor the elimination reaction. Okay. So again, heating will actually push it towards the elimination product. Okay. So small bases, nucleophiles prefer the E2, SN2. Hindered bases are going to go for that SN1, E1 preferred route. Okay, so for here, over here you got bromide, right? I said, okay, I want to see that SN2 product. Okay, so this is going to come here, kick away. But remember, with an SN2, we get inversion. So it ends up being that, Cl minus. Now we take that same product plus OH minus, and I say, okay, I want to see the E2 products. Okay, so here you're going to look at, is there a hydrogen here? Yep. Is there a hydrogen here? Yep. So if you're going to make the double bond between these two carbons, it's going to look like this. If you're going to use these two carbons, it's going to look like this here. And if you draw in the hydrogens, there. Remember, our leaving group was originally here. Okay, so we're just doing on either side. So, but this has two hydrogens. Oops, missed one. This was 3 hydrogens. So this is going to be the major product. Okay, so for acid catalyzed dehydration, it's the exact same mechanism. It's just this E1 E2 mechanisms. But what you have to do is you have to activate the OH group to make it into water. So with that, so since this is more of an E1 mechanism, it's gonna work best when that OH is hanging off of a tertiary carbon. Okay, so the first step is the oxygen is going to grab the H plus. Okay, to make what is a lone pair away from a water. So actually it leaves stuff like that. So this is for secondary and tertiary. Stuff like that. And then the water can come back, rip away the hydrogen, and then here it's like an SN2 type mechanism, rip away the water. Well, I guess it's E1, excuse me. And then collapse down towards the carbocation here to get and regenerate your acid catalyst. For primary alcohols, so you can't have it leave stuff like that. So because you're going to leave a primary carbocation, so what ends up happening is you do get the protonation first, but now you get more of an E2 type mechanism where you just grab this one next to it, collapses down, kicks away, and it's a terminal alkene, but that's okay. It's better than having a terminal carbocation. Okay, so rearrangements can happen with this. Whenever you have a carbocation, what happens is the molecule can shift where that carbocation is to get to a higher order. So if you make a primary carbocation, it can shift to a secondary. If it's on a secondary, you might get things moving around so that now you've got a tertiary carbocation, something like that. So, okay, so for here, when you get to this point here, so this is going to grab that hydrogen. The OH is going to leave to leave this secondary carbocation. Okay. So what can happen is this methyl group can shift over here, okay? And you would end up with CH3, CH, CH3, CH3. Now this carbon has 3 things on it, right? 3 carbons on it, right? 1, 2, 3. So this is tertiary. Well, this one only had 2. 1, 2. So this is secondary. So the drive to get the carbocation on the tertiary is that stabilization is what's driving this. Okay. After that, then the base can come in. You know, so if there's this hydrogen here, you can grab that and then collapse that down. Okay. You can do it on this side or that side to make your alkene. Okay. You can also do hydrogen shifts, so hydride shifts. Those are actually going to be preferable to a methyl shift because it's less energetic. The molecule, just because that weighs more, it's going to be harder to shift over a methyl group than a hydrogen. So for that, but if you need to do it, you need to do it. You can also get ring expansion, stuff like that. So you can break the ring and actually move this carbon-carbon bond. It's no different than a methyl shift, but you can shift this over, and you end up with this, which is 1, 2, 3, 4, 5, 6 six-membered ring. But now your carbocation is on a tertiary carbon. Okay. Now, the other thing we can do with alkynes, okay, is we can take advantage of the sp nature of a terminal alkyne. Now, you can't do this won't work on an internal alkyne, so not at the end because there's no hydrogen sitting on an alkyne. Okay, so this has much higher acidity than this one. So so from here to here, it's 10 to the 20, 10 to the 19. So 1 with 19 zeros over times more acidic. Going from here to here, you're 25, 10 to the 25th power more acidic. So 1 with 25 zeros behind it or after it. So like that, more acidic. It's not that this is twice as acidic. Nope. Each one of these pKa units is a factor of 10 because we're doing log 10. Stuff like that. So it's much more acidic. We can use this. Okay, so how do we make the alkynes? Well, basically what we can do is we can just do 2 E2 reactions. So if you have 2 bromines here, or 2 chlorines, you can just run a whole lot of base, and you can just do that E2 reaction twice. Okay, so you have a base here, grab this, collapse down, kick away to make your bromoalkene, and then just do it again. You know, your base comes in, grabs it, collapses down, kicks away the bromine. But notice how they're 180 degrees from each other, right? So with that, so you would end up with the alkyne. So you just do the E2 reaction twice. So the other thing we can do with this is we can actually use this as a nucleophile. Okay, so if you rip off this hydrogen here, because it's so acidic, throw in sodium amide with that to make this. This is a really nice nucleophile. And you can react this with a primary bromide to make a new carbon-carbon bond. Okay, so this one here, it's right in there, that's primary bromide, and so now you've added 2 extra carbons, which is what this course is about, right? It's about making carbon-carbon bonds. Okay, so if we want to design a synthesis, okay, so CH3, CH, right? We can rip away this hydrogen, throw in sodium amide. Oh, and what we're trying to make is CH3, C. Okay, and then basically CH2, and then that's a benzene, like that. So what we would do is we would then this would rip away this hydrogen, so it's going to rip this away and then move those electrons there. Okay, and then if we mix that, we're just going to go to the shelf and grab benzyl bromide. Okay, so there's CH2 bromine, right? We'll get this nice SN2 reaction there, and you'll make this. So where did this come from? Well, it just came off the shelf. That's what we needed to make this part. Okay. So these carbon atoms here came from here. These 3 carbons came from here. Okay. So one of the classic reactions with alkenes and alkynes is, we've already kind of touched on this, is hydrogenation. So by that, so if you take any alkene, just do a hydrogenation. So it's going to be hydrogen with some usually a metal catalyst. I usually do palladium on carbon. So by that, so it's a PD/C. So by that, but pretty much any of these sort of noble metal, or you can say catalysts here. So platinum, palladium, nickel, things like that. This is a ruthenium catalyst. That'll work. But basically, what you're going to be doing is you're going to be putting hydrogens across that double bond, and so it goes from a double bond to a single bond. Double bond, single bond. We talked about this earlier, right? So this is how they do hydrogenated fats. So usually most fats are cis double bonds, something like that. And so when you hydrogenate it, you're just putting extra hydrogens across that double bond. And so if you have polyunsaturated, it means you have multiple cis alkenes within that within the fat molecule. With that, so once you mix it here, it becomes solidified. Now the problem is you can have a degradation product where you have the trans because it's more favorable. Okay? And so the way this works is that when you put hydrogen in there, and I'm not entirely sure they know exactly how this works, but it'll absorb it. The bond actually breaks, and the hydrogens come and they'll stick out like this all around. The alkene will actually come in and on the surface, and it'll actually come in and grab those hydrogens and pull it away. So it's like, one I think about is if you take silly putty or something like that and you put that on comics, you kind of wiggle around and you peel it off, right? You get the comic strip behind. The other thing and so everything's on one side. The other thing you could do is if you have like a piece of tape, you want to pick up like some crumbs or something like that, you can put the sticky side down and come up, right? The crumbs are going to be on the same side. Stuff like that. So if you do this, it's a syn addition. Okay. So if you're adding groups across a double bond and they're both going on the same side, it's called syn. If they're going on opposite sides, one up, one down, it's anti. So this would give you like the cis product. This would give you the anti-trans product. Okay. This hydrogenation is a syn addition. So that if you're going to do the hydrogenation with an alkyne, it actually goes through this intermediate as the first hydrogen molecule, but then this is still reactive, and so it's going to go forward. And so if you just do a regular hydrogenation on an alkyne, you're going to get all the way to a single bond. So triple bond to single bond. Okay. But what if we need that? If we want to keep that double bond, well, what we can do is we can poison the catalyst, and it's usually we can throw in what's called a Lindlar catalyst, which is palladium with quinone embedded in it, or we can have palladium with barium sulfate added within it. And that basically what happens is it'll do that first step, go from alkyne to alkene, adding the hydrogens on the same side, but it's not, you've weakened it so much that it can't do the second step. It can't make it to the single bond. So it stops. And since you always add with hydrogenation, you add it to the same side, you actually end up making the cis alkene. Okay, but what if you want, so you can either do that, you can do a Lindlar catalyst. Again, you're going to be adding these across the double bond, on the same side to make the cis double bond. What if you want to do the trans? Okay, then you have to actually do a different mechanism. Okay, you have to go about it a different way, and you do what's called a Birch reduction. And so it's usually either sodium in the presence of ammonia in ammonia solvent, or lithium in ammonia. Okay, and so the way this works is, and so this would actually gives you the trans product. So the way this works is it goes through a radical reaction. I don't expect you to know this, but it goes through these one electron systems because the sodium and the lithium really want to get rid of that single electron so they can get into that noble gas configuration. So it gives it away, gives it the ammonia. The ammonia actually will solvate it, and it turns this brilliant blue color. But what ends up happening is you get this one electron system, and actually that's not a very good oh, yeah, got the hydrogen instead of hydrogen here. Stuff like that. So we'll talk about another reaction I was thinking about. But yes, so it actually, this is going to rip off the hydrogen from the ammonia, stuff like that, to make more sodium amide, and it goes more and more and more, stuff like that. So, but the net effect is that you get trans addition. Okay, so predicted product, right? So if you do regular hydrogen, and you can always assume that the hydrogen's in excess, so palladium on carbon. So it's just regular palladium carbon, so you're just going to add hydrogens, or else you go from a triple bond to a single bond. Okay. So with this one, now actually what I'm going to do, I'm actually going to redraw this to be more accurate, because it's a little bit easier to see like this. So remember this bond is, these bonds are actually 180 degrees from each other. So for that, so when we do the hydrogenation, but we're going to be doing it with a poison catalyst, the one with barium sulfate on there. What's going to happen is we're going to be putting these hydrogens on the same side. So you end up with, put the hydrogen, one hydrogen here, one hydrogen here. Okay. So if you're going to do this reaction, ooh, let me draw that. Wow. Okay. With the sodium and ammonia, right, now we're going to add one on one side, one on the other. Okay, so you're going to end up with you're going to end up with the trans product. One up, one down. Doesn't matter which side goes where. Stuff like that. So you're going to make the cis product here, and make the trans product here. Now, why are we doing this? Okay, so why are we doing synthesis? We don't, as far as a pharmaceutical application, it's incredibly important. And one of the stories is about Taxol. So this was developed, this was isolated from the Pacific yew tree, and it's actually isolated from the bark. It has anti-tumor activities, and I believe it's approved for, it's one of the main therapeutics for breast cancer. It's one of the first really good breast cancer drugs. The problem is, since it's isolated from the bark, if you strip all the bark off the tree, then you are going to kill the tree. You can get the Taxol, but you can kill the tree. So there was a crisis, right? Because yew trees take a long time to grow, like all trees. The problem, so what do? You can't just harvest all of the yew trees, because then what? You also can't build this entire molecule synthetically, because it's pretty hairy. It takes 20 or 30 steps, and each one's not great, and so it's just not going to be worthwhile to make it. It's just going to be too difficult to make it completely synthetically. But what somebody noticed is that just this part of the molecule here is actually present in the needles. And so what they do is they take the needles, extract out this part, and then they design a synthesis for this part, and then they join it up right there. And that we can do in a fairly straightforward manner. This is a much easier molecule to deal with, and we just attach the two together, and voila. But we need to know all of this type of chemistry to be able to design these syntheses to make enough of these to be commercially viable, to have good availability of these products. Like that. And so what we can do is we can issue what's called retrosynthetic analysis. This was developed initially by E.J. Corey at Harvard. He won the Nobel Prize for this. And so what we're going to, and now we'll talk about this more at the end of the next chapter, but what's happening is you start off with your target molecule, and you say, okay, what's the last step we need to put on? What functional group do we need to put on last? Okay, and then we think, well, okay, we can do that. Well, okay, so this is where we need to go through. Well, how do we get there? Well, we need to see, how do we get to there, and then how do we get here, and then so on and so forth, until you get down to a simple, inexpensive, commercially available material. Okay, so you actually kind of work backwards. How do we get there? And so you can look at a bunch of different precursors and how you would a couple of different routes. Now some of that, and so for this one here, we talked about this one here, right? You can you can go here, there. You can start off with this, something like that. And so if we need this molecule, we're going to have these two parts. So we're going to have to start with this. But how would you actually do the reaction? Well, you'd start with this and make this, and then go to here. So you then work backwards, or stuff like that. So you can sort of think about, well, how would we put this thing together, this molecule together? Well, we can make it here. You can put the bonds together here. We can make the bonds together here. You can make it here. And you kind of go through these routes, and you can say, well, this isn't going to be viable because it's on a primary carbon, but it's branched. Here, this is on a secondary carbon. The leaving group's on the secondary carbon, so that's not going to work. So like that. And so there are a couple of routes where, yeah, it could be. And so you assign a graduate student here, a graduate student here, and a graduate student here, and you go and you say, okay, try it. Which one, which is going to work the best? So like that. So that's how it works. And we'll talk about this more at the end of the next chapter. Okay, good luck.